All right, let's go ahead and get started. Again, thank you all for joining. We're really happy to have you here today. I think this is an excellent presentation, extremely relevant to the data landscape of today. Just a couple of housekeeping items before I have Deborah introduce herself in the session. We will leave a few minutes at the end for Q&A, so if you do have a question, please go ahead and put it in the chat and we will get to it at the end. This recording will also be available to you after the session. And with that, I will hand it over to Deborah.
Excellent. Thank you so much, Allison. Hello, everybody, and thank you for joining us today. The goal of today is to just actually have a nice, short, concise discussion on this accelerated computing tipping point that we are seeing and experience in the digital landscape today. And I want to start with a little GIF that I actually saw on LinkedIn. I joined Christina on a podcast series that she has called Dare to Data. And right afterwards, in the next week or so, she had published this to LinkedIn. And of course, everyone loves a good meme. And this poor little panda is trying to jump on this strangely configured swing and clearly not very successful. And her caption of "there's no AI strategy without a data strategy" kicked off quite the storm in the comments. And I actually thought this was really interesting because what was going on was a lot of data architects, data engineers, leaders in the data space actually felt extremely offended that we could even imply that someone doesn't have a data strategy today. My name is Deborah Leff. I've been in the analytics and data and AI space for over 15 years, 10 of those as an executive leader in IBM. And having spent so much time in this space, obviously, of course, we all have a data strategy. We've been on this journey for an exceptionally long time. So why now would someone imply we don't really have a data strategy or a data foundation is not in order? And I think this is like the first tip off that something is really changing in the market. And clearly, with the rise of Gen AI and the explosion of the use of AI and ML models, definitely it feels like something has been changing. And so, what we're experiencing right now is this paradox of what's happening with modern CPUs and compute. So right now, as you know, because it's been happening for so many years, data volumes are growing exponentially. The complexity of what we're doing with data, the queries that we're running, the transformations that we're running, just the number of joins that we're using is all escalating. And even though CPUs have been advancing, we are hitting this point where they just can't keep up with the demands of what people are asking them to do right now. And so this is why the digital landscape is actually reaching this tipping point. Scale is increasing, complexity is increasing, but the speed of which we can process data and get to end of data pipeline is actually decreasing. And at a time where we need this most, because everyone is pushing the envelope in this AI-driven world, now we are actually having the most difficulty and challenges that around speed and just complexity as well. And so this is creating this tipping point in this legacy computing. Now, this CPU infrastructure has been around for well over 40 years at this point in time. And the central core of a computer, the central processing unit, the CPU, is absolutely the brains of the computer. But what we have now today is the rise of the GPU, the graphic processing unit. You may be familiar with NVIDIA and their explosive rise in the last number of years. GPUs were originally created for graphics, as the name suggests, but they bring something to the table in today's data architecture that's really important. And the heart of why this is important is because typical CPU might have, even a high performance CPU might have 64 cores. Okay, I might cluster them together to have more cores, to be able to do more things simultaneously. But typically they're working in batches or in serial processes that just take time for them to churn through it. A GPU, on the other hand, has thousands of cores, 8,500, 16,000, which means that they can do that many actions simultaneously. Now, granted, they're not as sophisticated as what a CPU can do because that's where we process data, but GPU can do incredibly fast math and do many, many actions all together, resulting in this massive parallel processing. And so the way to think about this, on the left, we have all of this data, these very complex analytics actions that we're trying to do. And what it feels like right now in 2024 is that we're getting stuck in these bottlenecks. And my guess is you could probably think of a bunch of workloads from a very simple executive dashboard that just takes too long to load, all the way to someone is trying to make a critical business decision and it takes 2 days to get an answer that they really need, half a day from when they ask the question. And so that feels like being stuck in a traffic jam because those limited amount of cores can only do so much at a moment and therefore has to be processed serially. GPU throughput feels like being able to step out of that traffic and get into an HOV carpool lane with open road ahead of you where you can just fly through. And that's the difference between the difference between that type of processing and why we're starting to see a shift from CPU only processing to CPU plus GPU. And then just a little history about GPUs in general, right? They started for gaming. I'm sure we all played computer games as kids. Some even still play them today. They did extend into general purpose computing in the early 2000s. This marked a massive shift, even though they were really only confined to research at that point. And the real big breakthrough was when NVIDIA introduced CUDA, that then really allowed GPUs to be used as part of training models and processing data. And then we're all familiar with the rise of Gen AI. We never could process the amount of data necessary to train an LLM on a CPU. It would be physically impossible. We could launch a model today, and maybe our great great grandchildren could actually experience a fully trained model if we were doing it on CPU. GPUs are what make Gen AI even possible because you must have that massive throughput and that massive parallel processing in order to train those LLM models. And then you have newer technologies like SQream, which is where I'm from, that harnesses that even further to leverage GPU resources to process data directly. And what's really interesting to see is how GPUs have just taken off in the enterprise data center. It's only been within the last year that the sale of GPUs to the data center is up over 400%. And there is some really fascinating literature on how enterprises are using them today, from almost every single industry in a myriad of use cases. And we'll get into a little bit later. So let's talk about the impact of GPU acceleration. Okay, we all get it. They're fast, tremendous throughput, but what is the impact that can actually have? So here is an architecture I just picked banking, although you probably can put almost any architecture here as a proxy. You have the source systems along the left where the information is being generated and captured. That is being pulled together into a staging landing zone where there's a bunch of pre-processing happening, getting it ready for our analytical processes. And then those processes, in this case, what you see in your lower right-hand side of your screen are feeding specific ML models to get customer segmentation and behavioral scoring. And that is then feeding a whole bunch of different items throughout the organization, whether it's being fed into executive reporting, customer analytics, or other fraud detection and things of that nature. But if you take a look at the time of this pipeline, so let's actually say, let's go from data created to an executive report. Okay, let's just take a look at that as an example. Being able to capture all of the data as it's being created, getting it pre-processed and into a landing zone, this is actually a customer example, by the way, took 37 hours, okay? 37 hours just because of the volume of data and the nature of the pre-processing work. Get that into the analytical processes, another 11 hours to fully update all of the ML models, and an additional 2 hours to get that into the hand of an executive. Okay, so this is purely CPU processing with very, we would consider high compute resources. Best they could do with all of the tuning, all of the doing everything possible to try and make it faster. This is actually the best that they can do. But by swapping out some of those CPU resources for GPU resources, you can have a massive impact on that end-to-end process. So by handling all of the pulling the data together, getting it into a landing zone, doing all the pre-processing, reduced by 80%, simply because we're stepping off that congested highway and moving into that passing lane, the carpool lane, reducing the time it takes to update the models by 64%, reducing the time to get into the hands of an executive by 90%. And all that changed in this entire model was just bringing GPUs into the analytics processing zone. That means that end to end, a process that took 50 hours can be reduced to just over 11 hours. Okay, so massive acceleration in throughput, which, listen, if time doesn't matter, then maybe it's not necessary. But when speed matters, this can have a tremendous impact. And the interesting thing is, when people think GPUs, they think, well, GPUs are expensive, and they are. If you were to compare a single CPU versus a single GPU, yes, it's a more expensive machine, but you're using a lot fewer of them for a lot less time. And so in this particular case, it runs on 1/10 of the hardware and is a quarter of the cost. So not only massive acceleration, but massive cost savings as well. So let's talk about the cost efficiency angle, because that one's really, really important. And here's an example comparing cloud to cloud. So GPU processing, which in this case is SQream running on a hyperscaler, versus CPU-based analytical engine Snowflake. In this example, this particular query ran 20 times faster. So instead of taking 77 minutes, it takes under 4. And instead of it being a premium you're paying for that throughput, it's actually a fraction of the cost. Just over $10 for the item, down to just over $1. So a massive cost savings, simply because you've now opened up the throttle of being able to do much faster processing and use the compute resources for a fraction of the time. And obviously, that has a very, very meaningful impact when you're thinking about not just the productivity angle, but also the cloud compute program. And, I think over time, I mean, I've been in this space for a while, so from before, cloud adoption is what it is today. And so much of cloud adoption, the allure of it was this cloud elasticity, the fact that we can spin up the resources when we need them and spin them back down. But for a long time, they have been masking the challenges with CPU, because you can just scale up more of them, just throw more and more resources at them so that you can get to the end of job in the time frame that you want, if you can, because sometimes it's not as fast as you want. But by increasing cloud resources, that also means you're increasing cost. And I think I'd have to say the theme for 2024 across so much of the marketplace this year has been, how do I right size my cloud costs? How do I make sure that we are leveraging our resources more efficiently? And we participated we actually sponsored a study not that long ago. And what was really interesting about this study is it talked about how frequently you have bill shock as an executive leader who is getting their cloud bills. And the way the question was structured on the survey, it asked, how often are you experiencing bill shock? Once a year, once a quarter, once a month, every other month, or more frequently like that? And when I first saw the question, I was like, okay, and then not, I don't have bill shock. And I was thinking, gosh, if you've already had bill shock, you figured out how to right size your enterprise so that it's within the budget that you expect. No one, I think, in the entire survey selected no bill shock. I think no one, if anyone, maybe with like a tiny, tiny smidge. And then what really was shocking were how many people selected on a monthly and quarterly basis. So that just tells me that no matter how much people are trying to control those cloud costs, they're still not what they're expecting. And it's that cloud elasticity and the fact that we need more resources because the data is growing and the complexity is growing. And so there isn't a status quo, it just keeps going up. And so this has become extremely important. So, in terms of unlocking the potential of GPU acceleration, I figured let me just flesh out the rest of the story. So, the architecture that we were just looking at, the 50-hour process that went down to just over 10 hours, is a large bank. They have 50 to 60 million daily active users on their online banking system. So, this is a very sizable amount of data. They've grown by acquisition, which means that there's many disparate systems in the organization. There's a lack of unification and a lack of consistent data model and schema, which means that all of that munging and cleansing and transformation work has to be done in order to make that data useful, which of course contributes to that 37-hour delay. And the engineering team just felt like because they were 37 hours to just get to here's what happened today, they no matter what felt like they were always 2 days behind. And I think this is something that I hear very often from people that we speak with is that this drinking from a fire hose in data architecture and data engineering is just keeps going. It started 20 years ago and it really just doesn't end. No one ever gets ahead of it. But in an age where data and data projects have become so mission critical, they drive our competitive advantage. They help us identify net new revenue streams. There is such a strategic advantage to be have from data and analytics that this feeling of we're always being responsive and we could never be proactive is something that just really frustrated them. They really felt like they could do so much good for the organization if they could just get into a place where they could be proactive instead of just this drinking from a fire hose. And this was a very big component of what led them to go into the market and look for something else. Like there has to be a better way. It can't be just us. And that's how they stumbled upon GPU acceleration. And what they got from it were wholesale accelerated pipelines, the ability to enrich data, both with internal and in third-party data, things they couldn't do before, they just didn't have enough time, to be able to kind of increase the complexity of things that they can do. Now, if you work with data, you know that there's a limit to how many joins you could put into a specific query, because if you put too many, your system is just going to spin, 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 and then fail. And so that means that a practitioner who is working with data knows where those ceilings are and has to, on purpose, excuse the expression, but dumb down a query just to get it to run, or chunk down the data if the data is too large just to get it to complete. And so they really felt like all of these things were really working against them and not allowing them to get to deeper and deeper insights, which they felt are there within the data. And for some of their fraud detection, making sure they can get to deeper analytics has a very direct impact on their ability to reduce things like false positives for fraud, which then kick off a whole nother work cycle of trying to then determine, is it really fraud, and like disrupting workflows, things like that. So if I had to kind of skate by, like what are some of the types of things that GPUs impact in an organization? I'm going to say, well, let's go back to a lot of the promises we've been hearing in the world of analytics to the left of this white line: faster, better, cheaper. Because as long as I've been in analytics, I've seen products that are promising these things. I think that a lot of what's been going on in the world of CPU is incremental change. Things are getting little incrementally, bit by bit better. GPU comes in and they offer something dramatically different. It's just a completely different way of doing things. So on faster, you're really talking about increasing your decreasing your time to value, being able to eliminate bottlenecks that are related to latent pipelines. So any places where things are slowing down because it takes too long to fill in the blank, move the data, process the data, transform the data, enrich the data, all of those specific bottlenecks completely can be addressed by bringing GPU resources to that bottleneck to dramatically overhaul your ability to drive throughput. Fast query processing. This has a couple of impacts because it's not just getting to the answer, it's also about time. If I have a team of analysts and they're waiting 2 hours for a query to finish processing, they're either just going to go take a long lunch, or they're going to stop and work on something else, or they're just going to sit and wait for it. But there's a dramatic impact to productivity if practitioners are not just sitting and waiting for queries to complete. Not to mention, data scientists tend to get into this flow. They're like in the zone, interrogating their data. There are some studies that show that when that's disrupted, it could take a good 25 minutes just to get back into that same zone. So anytime that you have this massive stop where you have to wait for something, whether it's because you had to go to a data engineer to get something, or you're waiting for a long running query, not only do you have to wait the time to get to that result, but another 25 minutes to get back into that zone that you were in when you got disrupted. And for a data scientist, them using GPU-based tools means they can do data prep themselves. They can do things that they would otherwise need a data engineer to do in the CPU world, which has a very dramatic impact on model development and training. So faster is huge impact on time to value, and better means we now open up this world where we actually get much deeper insights. I don't need to constrain the size of the data set. I don't need to limit the complexity of the query. I don't need to rely on a data engineer. I can do that myself. I can stay in my zone. All of these things lead to much, much deeper insights that then make for more successful AI and ML programs. And on the cost perspective, I mean, you would think all of these things, that the better time to value and the deeper insights would come at a premium. And the most astounding thing to me is that it actually comes with a dramatic cost savings. Less hardware, less compute, better leveraging of your internal resources. But then we've got this little category on the side. And this one is actually very interesting because for every organization, there are always going to be things that someone would like to be doing that they actually can't. And being able to flip that switch of it's not possible or it's not feasible for us to do something, and then be able to light that up can be really impactful. So, for example, we have a customer. They are using SQream to optimize the yield of a factory, which is great for CPG companies or any type of manufacturing companies. But they're collecting all of the sensor data that's coming from all of the instrumented machines in their process. And that data was just too big. So the best they could do was analyze some of the data over 9 months. But they really felt like they were missing insights. And so they wanted to be able to analyze all of the data going back 3 full years. And that's exactly what GPU acceleration allowed them to do, to do something that physically they couldn't do. Now they do to drive better results. So whether it's the data is too big or the query is too complex, actually the same customer, as soon as they went live into production, called us and said, "You're not going to believe this, but we just saw a query complete that used to run for 2 weeks and fail." Can you imagine watching a query, like waiting on it for 2 whole weeks and then fail? And it completed with GPU acceleration in just 30 minutes. And they're like, "That's amazing." We're like, "That's amazing." They're like, "That's not the best part." The best part is there's a lot of other things we wanted to try, but we didn't dare. Because if that query failed, this other stuff we wanted to do just wasn't going to complete. And so we didn't even bother trying. So GPU acceleration completely lifted off these limitations where they just felt like, why bother trying? Because our systems couldn't keep up with our analytics imagination. And so that's a really meaningful thing that GPU does to unlock all of this incremental value. And so when it comes to leveraging GPU resources, we always say start with the end in mind. That's the best way in an AI-driven, ML-driven world, is start with what are the outcomes. Some of the conversations that we have with people are strictly a cry for help. Please help me lower those cloud bills. We can't keep up with these cloud bills. How can we leverage GPU resources to just right size our analytics in the cloud? And that's perfectly valid. Others might be, we have to get to end of job. Actually, having a conversation with a customer yesterday who is saying they've identified a new workload. It's compliance related. And right now it takes 2 full days for them to get to the answer that they need. And they are out of regulatory compliance. They must have that answer within a half a day in order for them to be compliant. And so there are always going to be times where a faster data pipeline has a meaningful business impact. And one of my favorite things about this is that GPU acceleration has the ability to be additive onto a legacy pipeline without breaking it. So a lot of times when people think, oh, we have to improve the pipeline, it's a big project to essentially re-architect it and then do this massive implementation. Instead, you can leverage GPU resources almost like a turbo button that you're dropping into an existing legacy process to make it faster. And that's pretty cool. Rapid innovation. I mean, this one, data scientists everywhere should be using GPU acceleration, not just to train models. Absolutely, you could use GPUs to train models. That's super important. And if you're using Rapids today, this is a phenomenal complement because you already know the impact that it has. But being able to use it for all of the data prep has a dramatic impact. Where if model development, it takes 50 to 80% of the time to develop the model, to prep the data for that model, you can collapse that by up to 90%, which is just a huge impact to accelerating ML development in an organization. And then, of course, you have the quality and the productivity aspects that are very meaningful for an organization. And just some, use cases that we might see. I know we have people from a mix of industries when I took a look at the list before our call today. But there are always both strategic and even non-strategic. Executive reporting may not be the most strategic thing, but it's kind of annoying to have to sit and wait for that spinner forever to get your results prepared for you. So anywhere from something as like super strategic as being able to have regulatory compliance in a specific workload, all the way to we just want our reporting faster so that we can be more nimble and more agile, and everything in between. And lastly, I just want to leave you with there is an article published on harassis.org that talks all about the accelerated computing tipping point and how GPUs have really entered the scene and are driving dramatic change. I will go ahead and actually ask Allison to just maybe we drop that in to the chat in case anyone is interested in it. Every organization today should really be thinking about where GPUs are coming into their environment. And if I think I don't want to leave you feeling like GPUs will replace CPUs, because if you think about it, CPU is good for probably the majority of the workload, 70, 80% of what you're actually doing. The best way to think of it is like a car. Like I live in New Jersey. New York is 15 miles away. If I want to go into the city, I'm going to take my car or an Uber, a car. That's going to be the most efficient way for me to get from my home into Manhattan. But if I have a conference in Las Vegas, I could take the car. I could drive in. It will take me many days. It'll be long and painful and expensive. Or I could go buy myself a seat on an airplane and be taken there much faster for much cheaper. And so this for me is like the way you think about GPUs are not coming to replace our CPU infrastructure. They're here to complement it for the times where you are trying to do something where now the CPU is actually just not best fit for. And SQream has a very interesting patented technology in that we allow for workloads that typically only could be run on a CPU to be run on a GPU. I'm going to invite you, if you would like, to check it out. Very much works seamlessly within an architecture. But if you'd like more information on GPU acceleration, how to put it to work, what might make a good use case, I encourage you to reach out to us or to go explore some links on our website where you can actually just try it out for yourself and like see what it feels like to go from stuck in traffic to getting into that HOV lane, hitting the gas, and flying through.
Thank you so much, Deborah. That was excellent. We did have a couple of questions come through if you have an extra minute or two. Um,
Sure.
First question here is, what technologies might this typically replace?
Oh, it's a great question. So I would say that GPU acceleration is not necessarily meant to be a replacement. It's meant to be highly complementary. So, for example, I'll go back to the example that we just did in Snowflake. If you are an enterprise that is using Snowflake, that's not going anywhere. You are likely using that for the enterprise. It's really important to the enterprise, and you are not going to be disrupting that. GPU acceleration with Scream Blue could be used side by side in complement. It has a Snowflake connector, as a matter of fact, where when you have pre-processing jobs that are just costing a lot in Snowflake because they are happening on CPU resources, and what that job needs is kind of outgrown what CPU does efficiently, you could go ahead and use Screen Blue, grab that workload, process it on GPU, and just return the results back into Snowflake. And so highly complementary, not really meant to replace. Um, but if you did twist my arm and say, okay, really, but like honestly, what does it replace? I would say ETL tools. That's probably where it's going to have the biggest impact, because transformation and enrichment on GPU is just going to be far faster and far more efficient and effective than is going to be on CPU. Smaller jobs, probably not. But the second you get into any latency or level of complexity, it's likely that is where it could potentially fit in as more of a replacement. But again, really meant to be complementary.
Thank you. And second question here, does this have to be deployed in cloud?
Oh, it's a great question. No, it doesn't have to be deployed in cloud. Scream makes GPU data processing available wherever you are. So if you are running on-prem, these resources can be deployed on-prem. If you are running in a VPC, they could actually be deployed into your VPC. So if you're using AWS, Azure, and you want that directly into your VPC, they can run there as well, or they can be available via public cloud with Screen Blue. So it's really just depends on where your center of data gravity is and what then becomes the most efficient deployment of that. And we work with companies that could be a police force that has very sensitive data completely just disconnected from the internet, and it absolutely must be on-prem. We support cloud at customer with some of our hyperscaler partners, as well as pretty much anything that you're running.
Great. And we had one come in just now too. Does Scream have an out-of-the-box connector for Snowflake?
It does, actually. Yes, it does. It does. We listen, we love Snowflake. Snowflake really, came in and changed the landscape. But many of the workloads on Snowflake, especially if you just take a look at what is driving up, like, the 80/20 rule, like what 20% of your workloads might be driving up an outside share of your compute. A lot of those workloads are really ripe for GPU acceleration. And so, yeah, we have a seamless integration into Snowflake. And if that's something you want to explore, it'd be a great thing to take a look at.
Okay, and that leads in to the very last one. What do I do if I want to try it out?
Oh, well, so the easiest thing to try out would be Screen Blue, because that's our public cloud offering. I can go ahead, Allison, if you don't mind, if you can just maybe drop in
Mhm.
the link where you can go ahead and request that on our website. You've got my LinkedIn right here. So if you want to take a little scan of my phone, you can message me. I'll be more than happy to set you up. We do start with a bit of a conversation because GPU is still a little bit new. So we just want to make sure that the workloads that you want to test are actually good fits for GPUs. And so we would just have a conversation with you, get you set up, and just go ahead and support you testing it. But absolutely, you can. Anyone available on our call today, we will offer $3,000 in free credits. You got a month to burn them up, but that's more than enough to go take a bunch of workloads for a test drive and see what it feels like to hit that open road.
Amazing. Thanks so much, Deborah. Thank you to everyone who joined today. We hope you enjoyed the session. This will be available in recording. We will send it over to you within the next day or two, and we will see you in the next one. Deborah, thanks again.
Thank you. Thank you, everyone.
Thanks. Bye-bye.